To discuss the physiology, we are going to make use of this diagram, where pulmonary circulation is shown here at the bottom, followed by alveoli in the middle, and then your airways and whatever mechanical tubing you have your patient connected to. Finally, all of this is in line with the carbon dioxide detector shown here at the top. In order to get CO2 to register, 3 things need to happen physiologically. First, we need to produce carbon dioxide in the peripheral tissues through aerobic metabolism. Second, we need pulmonary perfusion. We need all of that CO2 to actually circulate to the lungs. And finally, ventilation. Not only do we need carbon dioxide to diffuse into the alveoli, but also to make it up to our detector. Graphically, we get something that looks like this, where a plateau is formed during expiration, and the end tidal CO2 is recorded at the end of that plateau. During inspiration, the reading should be 0 because typically we are breathing negligible amounts of carbon dioxide. As a reminder, our carbon dioxide can be measured through the artery as well, and comparing these values can be valuable. Of metabolism, circulation, and ventilation, it is metabolism and ventilation that tend to make the end tidal and the arterial CO2 go in the same direction. What I mean by that is that anything that causes the arterial CO2 to go up, such as hypoventilation or hyperthermia, will also cause the end tidal to go up. The reverse is also true, in that hyperventilation or decreased metabolism, such as hypothermia, will cause both the end tidal and arterial CO2 to go down. Circulation can be more of a wild card and can actually make the end tidal and arterial CO2 go in opposite directions. You see, end tidal CO2 tends to be a little bit less than arterial CO2, and this gap can increase anytime we decrease the pulmonary perfusion or add alveolar dead space. To demonstrate this, let's add some dead space to our diagram and see what happens. On the right, there's no alveolar CO2 because there's no perfusion to this alveolus. On the left, the alveolar CO2 is reflective of the arterial CO2. Once these two mix and make it to our carbon dioxide detector, there's a substantial amount of dilution and the end tidal CO2 decreases significantly, causing a large gap between the end tidal and arterial CO2. Alright, now that we have some physiology under our belts, let's take a look at some common patterns that we're going to run into in the ICU. This one you may recognize. This is a normal capnogram, but let's review it for a little bit. Notice during inspiration, we're breathing negligible amounts of carbon dioxide and the reading should be 0. During expiration, we form a plateau that's almost flat but not quite, and we measure the end tidal CO2 at the end of expiration. And now let's compare the normal with our first abnormal example. Now this starts off looking normal enough, but notice that the end tidal is gradually decreasing. This can happen in any situation that causes the arterial CO2 to decrease, such as hyperventilation or a decrease in metabolism. But remember, the end tidal CO2 can also go down by anything that causes an increase in dead space, such as decreased cardiac output, a pulmonary embolism, or hyperexpanded alveoli. Our next example is basically the complete opposite. You'll notice a gradually increasing end tidal CO2. So this can be caused by anything that increases the arterial CO2, such as hypoventilation, or an increase in metabolism, such as hyperthermia. You'll also notice that the end tidal will go up anytime that you give your patient exogenous bicarbonate, such as a bicarb push. Our next example starts off looking just like the previous one, a gradually increasing end tidal CO2, but here's the difference. The end tidal isn't returning back down to 0 during inspiration. Why? It's because the patient is rebreathing. The patient has too much mechanical dead space, or the expiratory valve is not working, causing the patient to rebreathe all their previously exhaled CO2. The point being, if you see a waveform that looks like this, there may be something wrong with the ventilatory circuit itself. Our next example has a completely different waveform. We've lost our nice plateau, and instead it's been replaced by something that looks more like a shark fin. You may be thinking to yourself that it looks like it's taking a very long time for alveolar carbon dioxide to make it up to the detector, and that's exactly what's going on. There is an airway obstruction in this particular case. Most commonly, this is caused by a small airway obstruction such as COPD or asthma, but this could also be due to a very significant large airway obstruction such as a mucus plug, foreign body, or severely kinked endotracheal tube. Now this waveform starts off looking fairly normal, but eventually we're going to lose that nice plateau. What's going on here is alveolar carbon dioxide is not making it to the detector. Instead, it is actually leaking outside of the circuit. You get this if you have a tracheostomy cuff or an endotracheal tube cuff that's poorly inflated or blown, or perhaps you have a supraglottic airway that's not fit correctly. In any case, this is a leak in the circuit that should probably be addressed at the bedside. For our next example, I want you to imagine that you just intubated a patient and you used paralytics, and let's say 45 minutes or an hour have passed and the paralytics are starting to wear off, and the patient is starting to try to initiate breaths but isn't strong enough to trigger a full breath. What you're going to see is you're going to see a little cleft in the plateau. This is called a curare cleft, and is seen anytime a patient is making an inspiratory effort but is not strong enough to actually trigger a full breath on the vent. And finally, we are back to a waveform that should look fairly familiar. This is the waveform from our case, the one where we should be asking ourselves, is this normal or not? This is an important waveform because it could represent a lot of bad things happening. If you have a spontaneously breathing patient, this could represent apnea. This could also represent someone who is disconnected from the ventilator or the endotracheal tube is dislodged. And in worst case scenario, such as our patient, this could reflect a cardiac arrest. It should come as no surprise that a sudden drop in your end-tidal CO2 to 0 could represent a cardiac arrest because this is the ultimate in terms of dead space. There is no pulmonary perfusion that is occurring during a cardiac arrest, and therefore no carbon dioxide making it to our detector. With all that said, let's talk about how to use capnometry to manage our coding patient. Once you start CPR, you should be restoring pulmonary perfusion to some degree, and this should be reflected by an increase in your end-tidal CO2. This can also provide a goal for you. You want your end-tidal to be at least 10, if not greater than 15. And if you notice that your end-tidal CO2 is drifting downward, such as in this case, it's probably time to change out the person doing CPR. On the contrary, if you notice a sudden increase in your end-tidal CO2, then the patient probably regained a pulse. I particularly love capnography in the immediate post-arrest phase because I know that as long as my patient has measurable end-tidal CO2, they also have spontaneous circulation. This concludes our review of waveform capnography. I hope that you have found it useful. Thanks so much for tuning in, and until next time, this is Zach Fulkerson. So long.